Section 13.5 is called number of poles and synchronous speed. And it was an interesting thing. Soon after the discovery of the AC induction motor, it was found that by increasing the number of poles, the synchronous speed, the speed of the rotating magnetic field, actually decreased. Okay, so if the magnetic field synchronous speed decreases, of course the rotor speed is going to decrease as well. But you know, this interesting idea here, we add poles to the motor and the speed goes down. Okay, so let's explore why that happens as we create this body of knowledge in understanding this AC induction motor, and also going to introduce you to the primary fundamental equation in chapter 13, equation 13.1. Okay, so we're going to explore this in terms of not a two-pole motor, but let's look at a four-pole motor. All right, and so how is this thing constructed? All right, so the way this is constructed, instead of, you know, each pole covering 180 degrees, what we end up with is this is group 1, and this is group 2, and each group there, each of the 4 groups all cover 90 degrees across. Okay, now the groups, the groups 1, 2, and 3, 1, 2, 3, 4, they're all connected in series, and in such a way, you know, they produce these magnetic forces, you know, that operate, you know, in opposite directions, and all that particularly gets in the way, you know, the construction, the way things are wound in current direction and so forth and so on. But ultimately what you end up with, you know, if I take a snapshot of this, you know, I've got south, north, south, north across there. Okay, so in other words, when the current IA flows into the stator winding of phase A, it creates 4 alternate north-south poles. Okay, I've got 4 alternate north-south poles. Now, the windings of the other 2 phases are displaced from each other by a mechanical angle of 60 degrees, okay? And so I could add the other ones, and let me highlight, let me get a little, let's see, can I get thinner with this? Let me try this. So as I look here, okay, here's A, right? And then group 4, and group 1, group 2, group 3. Okay, so that is for phase A. And then what I do for the next one is I offset it 60 degrees from here to here, and then I would add, you know, group B here. All right, and so that's going in like this. And then finally, I would add group C here, and that is showing in like this, okay? And so, you know, that symmetrical arrangement of the pole groups across there. And so, you know, each one is separated by a mechanical angle of 60 degrees. When the Y-connected windings are connected to a 3-phase source, a revolving field having 4 poles is created, and the field rotates at only half the speed of the 2-pole field, okay? So by increasing this from 2 to 4, the speed has been cut by 1/2. Now, in a minute, we're going to show why that exactly is that way. So, you know, stay tuned for that. Moving on. All right. And so as we increase the number of poles, provided there's enough slots to lay those coils in, you know, at some point it becomes physically restraining to try to, you know, increase that. And that's another reason why the more poles you have, usually the more expensive the motor. But, you know, you can I think, get to a point to where you could see, here's an 8-pole motor, and so each group is covering, there's 360 degrees, 8. And so as I look at this thing, right, I look at this, and I look at A. Let's see, what have we got here? Here's the A's. We can see that there are 8 of those across there. You can count those and see that there are 8 of those. And each one of them, 8 into 360, would be covering 45 degrees, each one of them. Okay? So suppose the current in phase A is at its maximum value, the magnetic flux is then centered on phase A, and the north-south poles for this 8-pole motor would look like this. Okay? So, I'd have south-north, 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 south-north. So this would be the magnetic flux distribution across there. And so in comparing the two figures, from here to here, okay? So I'm going to start here, and then I'm going to go a half cycle through, and when I do that, a half cycle later, the current in phase A will reach its maximum negative value. And so what happens, what I'm trying to get to is that the north-south designation for the poles changes, right? So what was south here, is now a north pole here, okay? So that is just because of the nature of that sine wave and it going positive and negative and talking about direction and the designation of the flux, north-south designation for that. So that's just, a way that it goes. So, the magnetic field has shifted by an angle of 45 degrees, and this gives us 45 degrees from here to here, gives us a clue in defining the speed of rotation. So the flux moves 45 degrees after 1/2 of these, right? So it would take 8 half cycles, 8 half cycles, because 8 half cycles at 45 degrees each to get one complete turn, okay? 8 half cycles is the same as 4 complete cycles, 4 of these, 8 half cycles, okay? I know I'm sort of being redundant and repetitive, but, just so that make sure that you understand that. So, on a 60 hertz system, the time to make one turn would be, on a 60 hertz system, it would be 4 complete cycles times the 1/60th of a second, or 1/15th of a second for this magnetic field to make a complete turn, right? As these rotate north, south, north, south. Okay, so it's going here, 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 until it goes completely around. Consequently, the flux would be turning at a rate of 15 rotations per second, 15 rotations per second, or another way to think of that, 1 minute has 60 seconds. So it would take 900 RPMs for this to make, it would be rotating at 900 RPMs. So I can say an 8-pole motor will turn at 900 RPMs. So the speed of the rotating field depends upon the frequency of the source and the number of poles. All right, so that's what we want to take away. The speed of the rotating field is dependent upon the frequency of the source and the number of poles on the stator. Using that same reasoning, we can prove that the synchronous speed is always given by our first and probably the most important equation in this chapter, 13.1, which says synchronous speed is equal to 120 times the frequency divided by the number of poles. Okay? Now, I want you to know why this equation works, but when you start to look at motor nameplates and you're going to see particular speeds on those motor nameplates, you can predict how many poles the motor has by looking at the speed on the nameplate. Okay? So, I think that's interesting thing to know how to do, but it's an even better thing to understand why that occurs. So I have a little example here. It says, say the synchronous speed of a three-phase induction motor having 20 poles when connected to a 50 hertz source. Okay, what is the synchronous speed? Okay, it's equal to 120 times the frequency, and in this case, that's 50. Okay, and then 50 times 120 divided by the number of poles, which would be 20. And what I'm going to get from that is 120 times 50. 120 times 50 is what? 6,000 divided by 20. And 20 into 2 into 6 would be 300 RPMs would be the speed of a 20-pole motor. Now, there's not a lot of 20-pole motors out there. Construction cost of that would be pretty high. Think about the density of that thing and trying to lay those coils out across that stator. It would be, difficult to actually build this thing. But this is the formula that allows us to tell what the synchronous speed would be at any frequency and any number of poles for that motor.